everyone. So, this is third lecture of week 11. The previous lecture we started with Karmaker's algorithm. We learnt how to convert a given problem to the canonical form, and we also learnt what is projective transformation. Okay. So, recalling that, so yeah, you can look at the screen and down what is canonical form and what is projective transformation. So, what it means is that we are going to solve a problem which is in this form, min C transpose x subject to Ax equal to 0, A transpose x equal to 1 and x greater than or equal to 0. Okay. And so, if you apply projective transformation just says that yk is xk inverse xk by 1 transpose capital Xk inverse little xk, and little xk is capital Xk yk by A transpose capital Xk yk, right. So, you can actually see that any point little xk is actually converted to 1 by n dot 1 by n, right. So, that is because recall that capital Xk is just the diagonal matrix of xk. So, capital Xk inverse xk will give you all ones. So, 1 transpose of all ones is n, right. So, you will have yk will be 1 by n dot 1 by n, which is 1 by n into 1, right. So, that is where you take transform xk to. So, if you recall in affine scaling method from xk we transform to all ones, right. So, here we are transforming xk's to all 1 by n dot 1 by n. So, you will always have 1 transpose y equal to 1 because of that. Okay. So, that is the difference. Okay. So, yeah, recall that you have this constraint, right. The equivalent constraint of A transpose x equal to 1 is actually 1 transpose y equal to 1. Okay. So, the transformed problem after, so this is the canonical form. The transformed problem actually is the following. It is min of C transpose xk yk by A transpose xk yk. Okay. So, I have just substituted x as, call it as xk, then yeah. So, this I have just substituted xk as capital Xk yk by A transpose capital Xk yk. Okay. Subject to the conditions that A into, yeah. So, again xk I will substitute this, but note that the denominator does not matter because the right hand side is 0. Okay. So, this just becomes A xk yk equal to 0. Okay. And so, A transpose x has actually become 1 transpose y, sorry. Okay. So, this gets converted to 1 transpose y equal to 1, okay, and yeah, this is y greater than or equal to 0. Okay. So, yeah, that is how it becomes. Okay. So, the transform problem is, though it appears very similar, okay, there is actually a very big problem that, I mean, maybe some of you might have figured out. You can see that the problem is no more a linear programming problem, right. Why is that? Because if you see the objective function, right. So, you have y is in the denominator also. Okay. So, this is min with respect to yk, right. This is a problem that is linear in the numerator and linear in the denominator, right. So, that means, yeah, this problem is no more a linear programming problem, but we want this to be a linear programming problem, right. So, that is the reason why yeah, the optimal value had to be 0, right. So, you might have wondered why we had this condition that the optimal value of C transpose x star, that must be equal to 0, right. So, why was this asked for? It was because, so if the answer is 0, that means you can actually remove the denominator, is not it. So, you can actually write this as, right. So, I mean you can transform this as min C transpose xk yk subject to A x k y k equal to 0, 1 transpose y equal to 1 and y greater than or equal to 0. Okay. So, because so if the optimal answer is 0, that means you have C transpose capital X k y k itself is 0, right. So, it cannot be otherwise. Okay. So, that is the reason we want the optimal answer to be equal to 0. Okay. So, again we will see how to get around this anyway. Thus, we will continue with this problem that you are minimizing C transpose X k y k subject to A x k y k equal to 0, 1 transpose y equal to 1, y greater than or equal to 0. Okay. So, one thing that you can observe now is that the transform problem is very similar to what you got in the affine scaling method, right. So, there also the transform problem was minimize C transpose x k y k subject to A x k y k equal to 0 and y greater than or equal to 0. You did not have this extra constraint 1 transpose y equal to 1, okay. But check where we have it here, the transform problem, right. So, yeah, we okay, I do not know if I had written this anywhere, okay, but the projection was, if you could recall, right. Yeah. So, you can observe that the transform problem is very similar to what you got in the affine scaling method, right. So, yeah, if you recall this step, right. So, this was what you had initially, right, and after doing the linear transformation you got min C transpose x y subject to x y equal to b, y greater than or equal to 0, right. So, that is when we derived this big projection that you have here, which we converted to x into A transpose mu minus C, right. So, this is very similar to what you have here, where you are minimizing C transpose x y subject to A x y equal to 0, but you have this extra constraint 1 transpose y equal to 1. So, that is the only difference, but otherwise the transform problem is exactly the same as what you had for affine scaling method, right. So, fine, let us go ahead with this. Okay. So, what we have done until now is that we have converted the problem to canonical form, used the projective transformation and have converged to this particular problem now. Okay. Now, starting at some point x 0, okay, we have to find a descent direction, right. So, now we starting at x 0, we find the steepest descent direction, okay, which is minus C transpose x, right. Yeah, that is minus C transpose x, no questions on that. Project it onto the feasible set, feasible polytope, right. Fine. So, if you recall the projection of minus C onto the null space of A, right. So, yeah, let us write that down. Projection of minus C to null space of A is minus of I minus A transpose inverse A into C. Okay. So, it is actually this into minus C, but yeah, both are the same. Okay. Now, we have to, so I mean following the same thing here. Okay. So, therefore, the projection of minus x c, because the transpose is x c, right, to the null of A x, okay, A x k, right. So, is minus I minus x transpose A transpose. So, that is x A transpose A x squared A transpose inverse and A x into x c. Okay. So, fine, I mean that is actually the same as yeah, as you know. So, yeah, this is actually minus x c, right, and yeah, this part is mu. So, x A transpose mu, right. So, that is minus of or rather if you take the minus in, it is A transpose mu minus C. Okay. So, that is projection of minus xc into null of Ax. It is all the same what we did in the affine scaling method. Okay. But we have to do one more thing, because we also have to project this to 1 transpose y equal to 1, right. So, what I am doing is that I am first projecting onto the space Ax k y k equal to 0, and then I am projecting again to 1 transpose, I should have written 1 y k, since I have written y k everywhere, right. So, I am now projecting it onto this matrix 1. Okay. So, yeah, you can say it is a vector, but it is also a matrix of size 1 cross n, right. So, consider this as a matrix. So, now projection of this x into, maybe I will write that down, what is the problem, projection of x into A transpose mu minus c to null of 1 transpose. Okay. So, this is the matrix whose null space we are projecting this onto, right. So, what should this be? This should be I minus 1 into 1 transpose 1 inverse 1 transpose into x into A transpose mu minus c, right. But what is 1 transpose 1? That is actually n, right. So, because 1 transpose is a row vector of 1 1 1 1 1 1 1, right. So, that is 1 transpose. You have n ones here 1 1 1 1 1, and 1 is the column vector of ones 1 1 1 1 1. So, 1 transpose 1 is actually n. Okay. So, use that here. So, you will just get I minus 1 by n into 1 1 transpose, okay, into x into A transpose mu minus c. Okay. So, this is the dk that we will be using. Okay. I possibly had to write xk and mu k. Okay. So, or I will just write as d. Okay. So, if you are wondering what this is actually the steepest descent direction minus c transpose x, which has been projected onto the feasible polytope. So, I have gone through quite a few steps, because I mean I am first projecting it onto the polytope Ax k y k equal to 0, and then I am projecting it onto 1 transpose y k is equal to 1. Okay. So, that is the reason we have a few steps written here, but yeah, the expression clearly is just I minus 1 by n 1 1 transpose into x into A transpose mu minus c. Okay. So, fine, yeah, that is the direction. So, what we have now done is we first converted it into canonical form, then used projective transformation and somehow made it a linear program, right. We have now we have a transform linear program in which we have started with an initial point and found the direction to travel. We also need to find the step size. So, that derivation I am actually not going to give. Okay. So, in fact, the choice of step size is one of the key reasons why Karmakar could prove that his algorithm converges in lesser number of steps, in fact polynomial in n, right. So, but nevertheless I will just give the value of alpha. Alpha will actually be 1 by 3 root n into n minus 1 into 1 by norm d. Okay. So, what you will actually have y k plus 1 as y k plus 1 by 3 root n into n minus 1 into d by norm d. Okay. So, this is something we will use in the algorithm. Okay. But the derivation of alpha I have not provided, that is, say, complicated. So, I am just leaving it. I mean, people who are interested can read why such an alpha is being chosen. Okay. And as I said, this is a key reason why the algorithm is converging in lesser number of steps. Okay, fine. Now, yeah, so after this you do the reverse transformation. Okay, so now we will write down the algorithm whatever we have done until now. Okay, just write down the steps, right. So, yeah, so we first converted into canonical form, right, and yeah, after this we did this conversion, which is yk equals xk inverse, capital Xk inverse little xk divided by 1 transpose capital Xk inverse little xk, okay, and because of which we got this particular form, which is min C transpose xk yk subject to A xk yk equal to 0, 1 transpose yk equal to 1 and yk greater than or equal to 0, right. So, and after this a fine scaling method, okay, mu k is ax k squared A transpose inverse ax k squared c, and again I have not written xk as diagonal of xk, but that is okay. And now yes, I can write dk as I minus 1 by n 1 transpose x into xk into a mu k minus c, and yk plus 1 is yk, which is 1 by n into 1 plus 1 by 3 root n into n minus 1 into dk by norm dk, okay, and xk plus 1 is nothing but the inverse transformation, which is capital Xk yk plus 1 by A transpose capital Xk yk plus 1, okay. So, yeah, and this needs to continue, right. So, now given that you have capital Xk, now yeah, do k equal to k plus 1, right, and continue this, okay. So, fine, yeah, this needs to go inside a loop, okay. So, fine, but I mean there is actually an issue which is regarding the stopping criterion, okay. So, of course, if I just want to write the stopping criterion, it is very easy, because we have assumed that the optimal value C transpose x star is 0, right. So, you can continue this until mod C transpose x k is greater than epsilon, right. So, the tolerance, right. So, if modulus of C transpose x k is less than or equal to the tolerance, you can stop, because yeah, you are converging near the answer, which is 0, okay. So, yeah, this is fine. So, but note that we have actually not solved issue of not knowing V star, right. So, suppose some genie comes and tells us that V star is the optimal value, then yes, I mean we would have converted it into the canonical form of our wish, right. So, the canonical form is of this particular form, where V star is required, so that the optimal value actually becomes C transpose x star equal to 0, okay. But if you do not know V star, right, many of the things actually go berserk, right, because suppose the value is not V star, let us say, okay. In that case, the first thing is the transform problem is no more a linear programming problem, right. So, I mean it turns out that the transform problem is a nonlinear programming problem, right. So, then I mean all of these methods need not work, that is the first problem. The second problem is our stopping criterion also will not work. The stopping criterion is that the modulus of C transpose x k it should be going closer to 0. So, if it is going closer to the right answer, which is let us say 10.57, okay, then we are never going to converge. I mean we are actually going to get into an infinite loop, right. The stopping criterion is never going to be satisfied. So, how to get around this? So, let us actually note that, yeah, so though we have written A transpose X as general as possible, right. The A transpose that we have here, right. So, where we convert the given problem to canonical form, right. The A vector is always n minus 1 zeros and a 1, right. So, that never changes. So, I mean since it is an n dimensional problem and I am introducing n plus 1, I have written it as x n plus 1, right. But in general, I mean if you consider the canonical form as an m cross n matrix, right, that is x as an n dimensional vector, right. So, your A is actually n minus 1 zeros and a 1. Okay. So, what happens here is that the transformed problem, right. So, this problem is what I am referring to, that actually becomes, right. So, the transformed problem, right, it becomes min C transpose x k into capital X k into y k by, this is A transpose x k capital X k y k, right. So, but A transpose as we know is all zeros and a 1, okay. That is A transpose, right. So, maybe I should change this here as well, this is A transpose, right. So, this into x k y k, right. Now, I will write this as objective function. Now, what is the denominator now? So, x k is a matrix of x 1 k to x n k with all zeros, right, and y k is y 1 k to y n k, right. So, x k y k is x 1 k y 1 k, x 2 k y 2 k dot 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 x n k y n k, right. Now, A transpose x k y k is just x n k y n k. Okay. So, the objective function actually becomes C transpose capital X k y k by x n k y n k. Okay. So, the nonlinearity comes only because of y n k here, right. So, now when you consider the transform problem, right. So, it is min of C transpose x k y k by x n k y n k, right. And so, suppose you had, so the C here if you recall, right. So, it has minus V star, right. So, the C that you have here, right. So, the C transpose is actually, you have C 1 dot 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 C n minus 1 and finally, you have a minus V star, right. The minus V star was corresponding to optimal value of the standard form, right. So, C transpose x k y k, since x k y k is as I have given here, right. You will just have it as summation C k x 1 k, sorry x I k y I k, right, sorry C I then, C I x I k y I k I equal to 1 to n minus 1, okay, minus V star x n k y n k, right. So, the objective function then becomes, okay, summation C I x I k y I k I equal to 1 to n minus 1 by x n k y n k minus V star. Okay. So, this occurs because of the special structure of A that we have chosen here, right. So, the A transpose that we have chosen here is of the form all zeros and 1. Okay. So, because of that we can write the objective function in this particular form, right. So, if you are trying to minimize this, okay, then of course, I mean you can see that this is actually a constant. So, I mean this can be thrown away, right. And now, minimizing this is equivalent to minimizing the numerator, right. So, I mean that is the reason why we are actually sticking to this even when you do not know V star. Okay. So, I mean what I have told you is how do you get around this the issue of using C transpose x k y k without knowing the value of V star, right. So, yeah, so that is one thing that we have got around. So, we also need to get around the stopping criterion, which I will actually discuss in the next lecture. Thank you.